Hi, it's Paul back again with a third and final script. This one showing you nice illustrations of the solutions to matrix differential equations. This is designed so that you can put in your own values and rerun the script, because there are lots of interesting things that can happen that the three examples I'm going to do don't cover in full detail. First, let's start with the case where we have a 2 by 2 matrix A with two real eigenvalues. You all know how to calculate the eigenvalues and eigenvectors for a matrix, so I'm going to construct the matrix A from the eigenvectors and eigenvalues. Then you can change these to other values. So I'm going to make a matrix A that has two eigenvalues, 2 and -1. Since the first letter of the English name of the Greek letter lambda is an L, I'll call these capital L1 and capital L2, and then I'll set up the corresponding eigenvectors V1 and V2. The matrix P is obtained by using the two eigenvectors as the columns. The diagonal matrix D is made from the two eigenvalues, and the matrix P inverse can be calculated by using the R function solve. So all I do is take P times D times P inverse, round off to 6 decimal places so I don't get silly things like 10 to the -16th power, and there is our matrix A. Now I want to show you how to interpret this as a differential equation. So I'm going to leave 4 units of margin on the bottom where I can put the equation, set up a blank plot, and then paste in the differential equation. So the equation that I'm planning to solve is x dot, the time derivative of x, is 0 times x plus 2 times y. The time derivative of y, y dot, is x plus y. So I have two quantities, x and y, and for each of them, the time rate of change depends on both the value of x and the value of y. If we had x only, this is precisely the sort of differential equation whose solution is an exponential function. And what's remarkable is this works even in the 2 by 2 or the n by n case. I can solve the equation by calculating the exponential of the matrix A times a variable t, which corresponds to time. So let's do that. It's a function of time. Remember that when you calculate the power of a diagonalized matrix, you only need one factor of p at the beginning and one factor of p at the end. Since the exponential function, defined by its Taylor series, is a sum of powers with appropriate coefficients, the same thing is true here. So the exponential of the matrix A is just p times the diagonal matrix whose two entries are the exponential of L1 times t and L2 times t respectively, times p inverse. Now that we've got that exponential, we can use it. I'll pick a vector x equals 2, y equals 0 to get us started. I will choose a sequence of times at which to plot the solution. I'll put these 1/10 of a second apart, going from t equals 0 to t equals 2. And for each of those times, I will plot a point that I obtain by multiplying the exponential of at times v0 and plotting the first and second components. And there's what it looks like. The solution scoots off to the upper right-hand corner, and after about 10 points, I get thoroughly off the screen. If I start with a different initial vector, say x equals 0, y equals 1, and plot the points, I've done that in green. They seem to be heading off in the same general direction. And now it's easy to see why that's so. Because if I had chosen as my v0 one of the eigenvectors, the effect of the matrix would have been just to multiply that eigenvector by some function of time, and the solution points would move out along a line or in along a line. Let's try that by plotting the points that I get using the eigenvector v1 as my initial condition. I'll plot those in red, and you can see those move out along the first eigenvector, the one with eigenvalue 2. Recall that the second eigenvector had an eigenvalue of -1 associated with it, and e to the minus something is always going to be less than 1, so it should come as no surprise if I pick that. The points move in along that blue line, and now you can sort of visualize where the black and green plots came from. Take the vector, resolve it into two components, one along the first eigenvector, one along the second eigenvector. The component along the red eigenvector gets multiplied by an ever-increasing quantity, that along the blue by an ever-decreasing quantity, and if we followed those black dots and green dots far enough, they would approach the red dots more and more closely. This matrix A can be thought of as defining a vector field. It takes an element of R2, turns it into an element of R2, but you can think of the element in the domain as specifying a position, and the element in the codomain as specifying a velocity vector associating a motion with that specific point. Let's define a function to plot that. I will take a times my point P and then run an arrow from P to P plus 10% of the velocity. That'll scale the arrows down so they look nice. And I also, by checking the documentation, discovered how to make the arrowheads a little bit smaller, choosing a length of 0.1. If you look at x equals 0, y equals 1, you can see the vector that was plotted for that point, and it connects the first green dot with the second green dot. Basically what that's saying is that to a first approximation, the velocity vector tells you how you move from one time to a time in the near future. What's fun is to do this for lots of points, x ranging from -5 to 5, y ranging from -3 to 3, and now you can see a map of this vector field. This is a vector field that specifies velocity as a function of position, and when we solve a differential equation, basically we are constructing curves with the interesting property that the tangent to the curve is always along the direction of the velocity vector. Those of you who take physics courses may say, doesn't that look awfully much like electric and magnetic field lines? The answer is yes. Okay, now let's try a different case where we have a repeated real eigenvalue, so there's only one eigenvector. The eigenvalue will be 2. The eigenvector will be x equals 1.5, y equals 1. And in this case, as I hope you recall, we can make a nilpotent matrix whose square is 0. The reason its square is 0 is both its image and its kernel are equal to the eigenvector. So the first application of n gives us something in the image. The second application of n, since that's in the kernel, maps that into 0. So I make the matrix n, and just to check that I've done it correctly, I write out its square, which indeed is the 0 matrix. So the matrix A is going to be a diagonal matrix whose two entries are the eigenvalue plus this nilpotent matrix. This is guaranteed to have a repeated eigenvalue of L equals 2. Set up a blank plot again. Write the differential equation at the bottom. This looks innocent enough. The time derivative of x is 3.5 times x minus 2.25 times y. the time derivative of y is x plus 1/2 y. How do we calculate the exponential? Well, we're calculating the exponential of a diagonal matrix plus a nilpotent matrix. This diagonal matrix is a multiple of the identity, so it commutes with the nilpotent matrix, and therefore the good old rule that the exponential of a plus b is the exponential of a times the exponential of b still works. All I have to do is exponentiate the diagonal matrix, which is trivial, and multiply that by the exponential of the nilpotent matrix, which is also trivial because when I use the Taylor series, all the powers higher than 1 conveniently disappear. They're equal to 0. So there's the exponential of the matrix A. Now let's start with the same old initial value. See what we get. Only 4 points stayed on the screen. Choose a different point. Get some green points. This time we have only one eigenvector that we can check, and if we pick a value that lies on that eigenvector, the points just move out along the eigenvector itself. But you would search in vain for any other direction for which this was true. That's a consequence of there being only one eigenvector. As I did before, I can also plot the vector field and draw a pretty map of it. Well, what's left? What's left is complex conjugate eigenvalues. I'm going to choose a real part of -1. This is going to give us solutions that spiral into the origin, and you might on your own want to try the same thing with a small positive value or with a 0 value. The imaginary part specifies how fast the solutions circle around the origin. Well, we know one matrix that has the complex eigenvalue A plus IB. It's the familiar conformal matrix. There it is. And this is as good a way as any to illustrate what happens in this case. So I will use C as my matrix A, clear out my plot, and put the equation at the bottom. X dot equals minus x minus 2y, y dot equals 2x minus y. How do I calculate the exponential in this case? Well, it takes a bit of fiddling with Taylor series to do this, but it turns out that what you get is the exponential of the real part times t multiplying a matrix where the identity matrix is multiplied by cosine bt, and a matrix which you might want to call J, which represents a 90-degree rotation, and whose square is therefore minus the identity, gets multiplied by the sine of b times t. So there's the calculation of the exponential of A. That'll work for any time. I'll pick an initial value. I'll plot the solution every tenth of a second from 0 to 6 seconds. And isn't that a lovely result? What happens is that the solution spirals around counterclockwise and heads into the origin. If I pick an initial value that lies on the y-axis, exactly the same thing happens. And if we draw a map of the vector field, you can see it circling around. Now let's make a different matrix with the same complex eigenvalues. It's not going to be a conformal matrix, though. Let me fix that. And you may recall that any matrix with complex conjugate eigenvalues can be expressed as P times a conformal matrix times P inverse, and furthermore, we can set up the matrix P so that its first column is the first standard basis vector. So, first column of P is the first standard basis vector. The second one I've normalized so that the first component is 1, and the second one is a quantity that I'll call P22. I've chosen the value 2 for it, rather capriciously. I invert that matrix, and my matrix A is P times C times P inverse, which will show up in our differential equation. So here's a new differential equation, but the matrix A has the same complex eigenvalues, so we should expect the behavior of the solution to be fairly similar. There's a line on which the second column of the matrix of P lies. That may turn out to have some geometrical significance when we do the plot. And now let's use this crazy exponentiation formula again to calculate the exponential of AT. I just exponentiate the conformal matrix, multiplying on the left by P and on the right by P inverse. Choose my initial value 2, 0, and you see again the solution spirals into the origin, but it does seem to move in along the direction of that second line, doesn't it? I'll pick another point, and again it seems to get onto that red line and then move in. Here is a map of the vector field, and you can see there are lots and lots of vectors that are approximately parallel to that red line. On your own, you might want to go back. Oh, I can't resist. I'll do one of these. So first I will save this. And then I will set A equal to 0, and then I'll comment that out. But now we've got a new value for little a. And we'll run through everything as before without commentary until we look at the results. The solution to this differential equation is that the points just go round and round forever in a circle. No matter what value I start with, the solution is a circle centered on the origin. And when I plot the vector field, the vectors in the field circle round the origin. Now we can make a different matrix that has the same complex eigenvalues, just as before. Clear out our plot. There is the special direction determined by the second column of P. And in this case, I get not circles, but ellipses. And to my surprise, the direction of the red line, I'm not sure is precisely the major axis of that ellipse, though it's close. And the same thing happens with a second choice for my initial value. And when you draw the map of the vector field, it again appears that the long vectors are parallel to the red line.